Yes, sir.
Okay, perfect. So, yes, good evening, everyone. This side Dr. Abhijeet, and welcome to yet another session of this 45 days to final exams, right? The MBBS final first prof exam, right? So we have initiated this intensive revision series, right? And today we are going to discuss about the carbohydrate metabolism 2. Right. So basically, what we are doing in this particular series, we are revising the most volatile topics, like the most potent questions for the upcoming exams, right? For university prof exams, right? That will be in August. So I will be discussing like question wise, and it will be like I will be discussing the entire concept in a very crisp, concise, and conceptual manner. Yes, over here, guys, I will be like discussing questions which has been like previously asked, right? The questions which have been asked multiple number of times in the recent few years, right? I will be trying to cover that. I will be teaching the entire concept of that particular question, right? So that these are the questions that I will be covering up today, guys. These are the questions that I will be covering up today, right? So we have like short essays and short answer type questions, right? In essays, we'll be just like trying to focus on the important aspects along with the cycles, and short answers will just I will show you how to write these short answers, right? So yes, apart from that, guys, like about the Oracle app, you already know we have the recorded classes, we have the live classes which are streaming live on YouTube also, as well as an on app also. We have the recorded practical sessions also, right? Even the exam module is there. Even you will get a hard copy set, which is like the notes are curated in such a form that it is like in the Q&A format, right? The question and the answer format, right? So yes. Apart from that, guys, these are the recorded classes which you can like get an access by just downloading the app. Yes, live classes, right? We have these, yes, exam modules, right? We have one-to-one doubt clearing session, and we have practical session as well, right? So yes, we have the question bank, guys. Question bank in which we are designing okay. In the question bank, guys, after each and every topic, you have questions from basic to advanced level, right? All the important previous year topic questions are there, right? All the important previous year topics are there, right? So basically, we have like basic one-liner questions also. We have like questions which are nowadays like more relevant. That is the clinical based questions also over here. Right. So that is the hard copies note set, and this is the basic subscription plan, which you can just see on the screen. And for additional discounts, guys, you can just use my code Dr.Abhijeet20. Right. Now, let us start with the very first question. That is the Cori cycle. Okay, now this particular question has been asked in January 12, revised schedule 33, and it is also asked in January 14, guys, January 14. So now what is this Cori cycle, guys? Let us first try to discuss in our own way, then I will come to what is like meant in the notes. Let us first understand what is this Cori cycle, or I can simply say this Cori cycle, it is also called as the glucose lactate cycle, the glucose lactate cycle. Now, guys, you already know, students, that okay, let us just suppose, let us take an example that if let us assume a condition that this is a skeletal muscle, right? This is a skeletal muscle, and you guys already know this skeletal muscle, if there is sufficient amount of oxygen present, okay, if there is sufficient amount of oxygen present, what will happen? The glucose will be converted to, yes, pyruvate, right? That is the simple glycolysis that we have discussed in the previous session. That is the simple glycolysis will take place. Now assume a condition, guys, assume a condition where the skeletal muscle, okay, where the skeletal muscle is exercising, right? Now I'm assuming a condition where there is no sufficient amount of oxygen available. Now I'm assuming a condition where there is no sufficient amount of oxygen available. So I can simply say that this is exercising skeletal muscle, right? Exercising skeletal muscle. Now, what will happen? Now, when you're doing exercise, all the skeletal muscles, the muscles which are attached to the bones, right? All the skeletal muscles, the biceps, triceps. Now, what is happening? There is not sufficient oxygen, guys. There is not sufficient oxygen, guys, right? Now, what it will do, it will undergo anaerobic glycolysis. It will undergo anaerobic glycolysis now. Now, guys, whenever there is sufficient oxygen, if there is like sufficient oxygen, what will happen? Aerobic glycolysis will take place. Aerobic glycolysis will take place. Now, there is not sufficient oxygen, guys, in a, let us suppose in exercising skeletal muscle, what will happen? What will happen, guys? This glucose over here. Let us just try to illustrate what is this, and please try to draw this. Whenever this question is asked, guys, the very first thing that you have to draw is this particular diagram. It's a flow chart. Okay, the flow chart is very, very, very important. Yes, and then you have to explain. Now, what will happen to the glucose, guys, over here? This glucose will be converted into pyruvate. This glucose will be converted into pyruvate. And because there is not sufficient oxygen, this pyruvate will be converted into lactate, will be converted into lactate. Yes, by the help of enzyme, yes, lactate dehydrogenase, right? Now, what will happen? What will happen? This lactate, okay, even guys, if there is not sufficient oxygen, guys, there is one more structure that is called as RBCs, right? There is one more structure that is called as the red blood corpus cells. Now, what will happen in this red blood corpus cell? Again, there will be anaerobic glycolysis. Glucose will be converted to pyruvate, right? Glucose will be converted to pyruvate, and pyruvate will be converted to lactate. Lactate in anaerobic glycolysis. We have already discussed this. Now, this lactate from the RBC, okay, where there is not sufficient oxygen, right? And from this exercising skeletal muscle, from this exercising skeletal muscle, they will now go and enter into the liver. They will now go and enter into the liver, guys. They will now go and enter into the liver. This is the liver, guys. Now, obviously, this lactate can get accumulated. It can cause lactic acidosis. Okay, but what is happening? This lactate, it is going because of the cycle, guys. This lactate is again going into the liver. So this lactate came here. Now what will happen with the help of an enzyme lactate dehydrogenase? Okay, we have an enzyme called as lactate dehydrogenase. What will happen? This lactate will be converted into pyruvate again in the liver. Pyruvate again in the liver. And this pyruvate, and you already know this is the process of gluconeogenesis, right? This is the process of gluconeogenesis. Now, when I say gluconeogenesis, guys, you already know it is the synthesis of the glucose from other substrate, new substrate, right? You're not taking glucose from the diet. You're not taking disaccharides from the diet, the maltose, sucrose, or lactose. You are basically generating the glucose from some non-carbohydrate substrate, such as pyruvate over here, So this pyruvate will undergo this gluconeogenesis and it will get converted into glucose. This will be getting converted into this glucose, right? So this glucose will be again going into the, okay, obviously I have not drawn this, guys, but just remember we have a blood vessel also in between, right? We have a blood vessel on also in between. This is the blood vessel, right? So to this blood vessel, what has come first? Yes, you already know we have the lactate, and this lactate has gone into the liver from the blood vessel, arteries, veins, right? And from this glucose, like from the liver, the glucose is produced, right, by the help of gluconeogenesis. Now this glucose will again come into the blood vessel, right? It will again come into the blood vessel. And from here, it will again go into the muscle. It will again go into the muscle, or it can again go into this. Yes, the RBCs, guys. So that is basically the simple representation, a cycle that has initiated from this exercising skeletal muscle or RBC where there is not sufficient amount of oxygen. They are converted into lactate, which goes into the blood vessel. This lactate goes into the liver, converts into pyruvate, and it undergoes gluconeogenesis. This pyruvate is a non-carbohydrate. It's not a carbohydrate, but we are generating carbohydrate from a non-carbohydrate substrate, that is pyruvate, and that is the process called as gluconeogenesis. Right? So this glucose lactate cycle, guys, let us now. Now, let us just try to see what they have written. So the Cori cycle, it is also called as the lactic acid cycle or the glucose lactate cycle. We have already discussed this, right? So what is this metabolic pathway where the lactate is produced? I have already told you from glucose, what is produced? Pyruvate. From pyruvate, it is the lactate which is produced. Okay, by anaerobic glycolysis. This is anaerobic glycolysis where there is decrease in amount of oxygen, where there are not sufficient levels of oxygen present. Now this glucose, it is transported to the liver, guys, right? It is transported to the liver. Okay, and then from the liver, basically glucose is generated and then it is transported back to the muscles, right? So basically, this all we have discussed. Yes, from bloodstream by transported to the liver, gluconeogenesis, hepatic, because obviously it is taking place in the liver. Gluconeogenesis, basically the pyruvate, it is getting converted to glucose. A non-carbohydrate substance is giving rise to the carbohydrate. That is gluconeogenesis. Gluconeo means new, something which is like not there. Okay, so yes. And that is again the cycle which you can see over here. That is from muscle to liver and from liver to muscle. So that is something which you have to remember. What is the importance of the cycle, guys? Very, very important. You have to mention it helps in the prevention of the lactic acidosis. Guys, obviously, I told you if this lactic acid get accumulated, right, it will be causing this lactic acidosis. Okay, and guys, remember it produces ATP, that is the energy currency of the cell, right? It is the energy currency of the cell, right? Energy currency of cell, right? And it is the important source for gluconeogenesis. Now, guys, imagine a condition where you are actually fasting, right? You are actually fasting. Fasting means not in the early fasting, guys, late fasting. Late fasting, guys. Late fasting, more than 16 hours of food. See, we have like 3 stages, guys. The well-fed state, when you have just taken the food, it is initially like 1 to 4 hours of food, right? 1 to 4 hours after food, when you have like consumed your diet, right? The breakfast, lunch, or dinner, like it's the well-fed state. Then comes the stage of fasting. Fasting is early fasting, guys. Now, obviously, after 4 hours, you will not start eating again, right? Whatever extra glucose is there, it has been converted into glycogen in the well-fed state. Now, in the early fasting, that glycogen which is stored in the liver will be broken down to release glucose for the energy, right? For doing work. So that is glycogenolysis will be taking place in early fasting. Whatever glycogen is being stored in the body, it will be broken down to release glucose, and that glucose will be providing energy in the early fasting, right? Approximately like 8 to 16 hours, right? Now, beyond 16 hours, that is the late fasting, guys. Yes, over here, guys, what is happening? You're not taking any diet, no food, you're not taking any, there is no glycogen left in the body now. Where the glucose will come from? Now the glucose will come from some other non-carbohydrate substance, that is the pyruvate, guys. And that is in the late fasting, gluconeogenesis will initiate in the body. And that is yes, that is one of the significance of these gluconeogenesis that you have to remember, right? In the late fasting, it helps us to generate the glucose to maintain the body requirements for the ATP, right? So that is about the Cori cycle. Now, guys, so this was our first question that we have already discussed about the Cori cycle. Now, this you have to write down and you have to first draw this particular flowchart, which I have also drawn for you people, and you can just this like almost the same, right? And please write it after this, the definition, the process, and the significance. That is how it has to be mentioned in points, guys, right? Now, coming on to the next question, guys. Yes. define anaplerosis. I have already discussed this in the last session, guys, right? The anaplerotic reactions of citric acid cycle, or it is, yes, I don't know why. We have already discussed this tricarboxylic acid cycle, right? Or we have also called it as the Krebs cycle, guys, Krebs cycle. Now, anaplerosis, it is defined as the reaction that can replenish the intermediates of the pathway. Obviously, this is a like cycle, guys, right? So there are various intermediates of this pathway. In simple terms, guys, it maintains the dynamic balance of an anaplerotic route in such a way that the concentration of the crucial but depleted intermediate remains as a constant, right? So let us just try to see, guys. There are four, and the question says you have to like describe any four anaplerotic reactions of the citric acid cycle, and these four reactions, guys, you have to first name them, right? How will you write that? There are four major anaplerotic reactions in the TCA cycle, from pyruvate to oxaloacetate, phosphoenol pyruvate to oxaloacetate, phosphoenol pyruvate to oxaloacetate, right? And pyruvate to malate. Okay. So let us try to discuss this one by one, guys, right? Now, guys, pyruvate to oxaloacetate basically takes place in the cells of the liver and kidney, right? Now, the enzyme that is required to convert this pyruvate to oxaloacetate, it is pyruvate carboxylase. Okay, pyruvate carboxylase is the one which will help in the conversion of this pyruvate to oxaloacetate. Oxaloacetate. You already know oxaloacetate. Now, guys, if this is a cell, guys, you already know we have the mitochondria. We have the mitochondria, right? And we have this oxaloacetate in the mitochondrial matrix. Now, this oxaloacetate is the intermediate of TCA cycle. You already know from pyruvate, basically what is formed, you already know acetyl coenzyme A, right? Acetyl coenzyme A. This acetyl coenzyme A comes in the mitochondrial matrix and it comes with the oxaloacetate, right? So oxaloacetate is basically an intermediate of this TCA cycle, right? That condensation, basically, they both combine. Oxaloacetate is 4 carbon, acetyl coenzyme is 2 carbon. They form a compound called citrate, guys, right? Citrate is a 6 carbon compound, right? So basically, that is something you have to remember. This oxaloacetate is an intermediate product in this tricarboxylic acid cycle or the Krebs cycle, right? So this enzyme is basically catalyzed by this pyruvate carboxylase, and it is most important part of the anaplerotic route or the anaplerotic pathway. Now, guys, coming on to the next one, that is phosphoenol pyruvate to oxaloacetate. Now, guys, basically you have to remember, guys, this phosphoenol pyruvate, it is basically getting converted into oxaloacetate, right? To maintain the steady flow of the anaplerotic reaction. So basically, this is taking place in the heart and it is also taking place in the skeletal cells. It is basically done by an enzyme that is called as phosphoenol pyruvate carboxylase, right? Now, over here, whenever this phosphoenol pyruvate, it is converting into oxaloacetate, guys, what will happen? GTP will be produced, energy currency will be produced, right? Guanosine triphosphate will be produced, right? So that is something you have to remember over here, right? So basically, if GTP is produced over here, it requires magnesium 2 plus, okay, as an intermediate cofactor, right? So that is something you have to remember, guys. The third one that you have to remember, it is pyruvate to malate, guys, right? So pyruvate, it is basically converted into malate. Okay, pyruvate is basically converted into malate by the help of an enzyme malic. Okay, and guys, remember that it uses NADP as the cofactor, right? It is basically using this NADP as a cofactor, right? So basically, this pathway is taking place in like eukaryotes, like all the cells, right? And the bacteria. Apart from that, phosphoenol pyruvate to oxaloacetate, okay, basically by the help of enzyme phosphoenol carboxykinase, guys, right? Now, remember, guys, it is basically, okay, now you have to learn the difference, guys, over here. There is an important distinction between the oxaloacetate produced by pep carboxylase that we have just discussed, and pep carboxykinase. Now, what happens in this reaction, guys? This oxaloacetate basically it is accompanied by the formation of GTP. Okay, it is accompanied by the formation of GTP. This takes place in like yeast, bacteria, and all those things, right? So yes, it is a junction between the glycolysis and the TCA cycle, right? So basically, phosphoenol pyruvate combines with this bicarbonate to basically form the oxaloacetate, right? Plus phosphate will be released. So these are actually the four anaplerotic reactions, and this is something you have to mention like this, right? So that was regarding the second question, guys. That was regarding the second question today. Now, coming on to the next question, that is, yes, the glycogen storage disorder. Now, guys, this is something very, very important. If you just see it is asked in December 6, revised schedule 2, January 17, revised schedule 3, January 2000, January 2003, January 6, January 14. So it is like one of the most important questions, guys, that you have to remember. Right, one of the most important questions, guys, that you have to remember. Now, guys, to understand this particular part, let us first try to make it very simple, guys, in the form of a flow chart, guys. Okay. Now, guys, you already know. Firstly, I have to synthesize from glucose to glycogen, right? Then we will be studying this no glycogen storage disorders, right? So from glucose to glycogen. From glucose, basically what is happening, we are activating the glucose. It is forming UDP glucose, right? That is something called as activation of glucose. Activation of glucose. Now from this UDP glucose, what is happening? The linear chain is formed, right? The linear chain is formed. That is by the help of enzyme glycogen synthase. Glycogen synthase, the rate limiting enzyme. This linear chain, it is basically getting converted into glycogen by the help of enzyme branching enzyme. By the help of enzyme branching enzyme, right? Now, what happens? This is we are from glucose. What we are synthesizing? We are synthesizing glycogen. It is forming UTP glucose. It is forming linear chain, right? And it is forming glycogen. That is the simple glycogenesis. Glycogenesis in very short, guys. Now, what is happening to this glycogen? Okay. Now, again, I have to like talk about this. Yes. Now, glycogen, it is basically getting converted into the limit dextrin. We have already talked about this. Yes, by the help of enzyme glycogen phosphorylase. Glycogen phosphorylase. Now, there is some enzyme that is called as the debranching enzyme. Debranching enzyme, right? Now, what will happen? This will convert this limit dextrin into linear chain. Linear chain. And this linear chain will be converted into glucose 1-phosphate, right? With the help of enzyme glucose phosphorylase. Phosphorylase. This glucose 1-phosphate will be converted into glucose 6-phosphate by the help of enzyme mutase. You already know glucose is a 6-carbon compound, guys, right? It's a 6-carbon compound. At first place, there is phosphate. Now, again, it has like the same molecule. It is glucose only, but now we are shifting this phosphate from first position to sixth position, right? So enzyme that is used, that is mutase. Whenever like one functional group is shifted from one place to another in the same molecule, that is the enzyme mutase that we have already discussed. And this glucose 6-phosphate with the help of enzyme glucose 6-phosphatase, it will be converted into glucose. Glucose, guys. It will be converted into glucose, right? So these are the intermediates which you can see over here. Now, guys, let us just try to discuss the disorders. Okay, let us just try to discuss the disorders over here. Now, guys, you can very well see if this particular enzyme is absent, okay, if this is absent, guys, then it will lead to type 1 disorder, guys. Type 1 glycogen storage disorder, or it is also called as von Gierke's disease. It is also called as von Gierke's disease. It is also called as the von Gierke's disease, guys. Obviously, if this enzyme is absent, glucose 6-phosphate will be never be able to convert into glucose. Glucose will not be formed in the body. Obviously, the patient will have low levels of glucose in the body, and that will result in hypoglycemia. Now patient will what have? It will have increased amount of glucose 6-phosphate. Obviously, in von Gierke's disease, you will see the patient glucose is not formed. The glucose levels in the blood will decrease. The patient will be suffering from hypoglycemia. In the patient's blood, you will see this glucose 6-phosphate is elevated. Obviously, because this enzyme is not working, that is glucose 6-phosphatase, help, which helps to break this phosphate group. Now, again, guys, another thing that you have to remember, guys, over here, if this debranching enzyme is absent, it will lead to type 3 glycogen storage disorder, or it is also called as Cori's disease. Okay, the linear chain won't be able to form, right? Now, guys, now, if there is deficiency of this glycogen phosphorylase, it will lead to type 6 glycogen storage disorder, and that is called as Hirsch disease, right? Hirsch disease, right? Now, guys, that is something you have to remember, guys, right? Now, if there is like no deficiency of this particular branching enzyme, guys, it will lead to type 4 disorder that is called as Anderson's disease. Anderson's disease, right? Now, yes, glycogen can also no get into the lysosome by the help of enzyme acid maltase. It will be like converted into glucosidase, right? So yes, obviously there will be something called as Pompey's disease in which the acid maltase or lysosomal glucosidase is absent. Okay, so yes, so this glycogen can also enter into the lysosome, right? In lysosome, basically we have an enzyme which actually converts this glycogen into glucose, right? So obviously that is the lysosomal glucosidase or acid maltase. Right now, remember, guys, if this is absent, guys, it will lead to Pompey's disease. Guys. It will lead to Pompey's disease, right? So that is something you have to remember, guys, right? No, that is something which is mentioned in this particular chart also, guys. That is mentioned in this chart also. Von Gierke's disease, deficiency of glucose 6-phosphatase, liver or kidney, hypoglycemia, I've already told you. Obviously, if there is low levels of glucose, oxygen, yes, there will be lactic acidosis, right? So that is something you have to remember. We have Pompey's disease. I've already told you acid maltase or yes, that will be absent. So the all organs with like lysosomes, right? Limit dextronosis or Cori's disease. Yes, I have already told you the branching enzyme. And how can you remember, guys? A, B, C, D. Okay, A, B, C, D. So Cori's disease, it is basically associated with debranching enzyme deficiency, right? Debranching enzyme deficiency, right? That is something you have to remember. Even the Anderson's, guys, if you can just remember, yeah, the Anderson's disease is basically, referred with this branching enzyme. You can see AB, Anderson's disease with this branching enzyme, right? Branching enzyme, right? Taking place in the liver. McArdle, muscle glycogen phosphorylase. Hirsch disease, liver glycogen phosphorylase. If in the liver, this glycogen phosphorylase is absent. If in the muscle, MEC, just remember MEC, muscle. Hirsch, liver, right? That is something you have to remember. And Tori's disease, deficiency of phosphofructokinase, right, in muscles and erythrocytes. That is something you have to remember over here, right? So this is in short essay that you have to write about glycogen storage disorder, right? Now, coming on to the next one, that is the uronic acid pathway, guys. Uronic acid pathway, right? You guys already know this is an alternative oxidative pathway for glucose. It is also known as glucuronic acid pathway. So it basically includes the synthesis of this glucuronic acid, right? pentoses are synthesized, important vitamins, and ascorbic acid, right? So you can just see this pathway, right? So yes. Now, what is the significance of this uronic acid pathway? That is the very first question that they have asked from us, right? It is basically asked in this January 9 revised schedule 2. Now, guys, remember it is an alternative pathway for oxidation of glucose. Over here, there is no production of energy. There is no production of energy, and oxidation of glucose takes place. Glucose is converted to glucose 6-phosphate, then glucose 1,6. Um, from this glucose 6-phosphate to glucose 1-phosphate. So basically oxidation of glucose is taking place, but over here no energy is being produced, right? Mainly glucuronic acid is used for the detoxification of drugs, foreign substances, and for synthesis of mucopolysaccharides. We have already discussed the heteropolysaccharides in detail, guys, right? So basically this glucuronic acid, which is now coming out over here, it is basically used for the synthesis of this MPS, that is the mucopolysaccharides, and even the essential pentosouria, the autosomal disorder. Basically, it is caused due to the enzyme L-xylitol dehydrogenase. Okay, so basically, administration of glucuronic acid increases the quantity of xylulose excreted. So that is the three significance that you can like mention over here in this particular question, right? So that is about the significance of the uronic acid pathway. Now coming on to the Rapoport-Luebering cycle, guys. Coming on to the Rapoport-Luebering cycle, and guys, you already know this Rapoport-Luebering cycle we have already like discussed a multiple number of times, right? Now this Rapoport-Luebering cycle, guys, you already know. Okay, now what is happening over here, guys? Now, it is a supplementary pathway to glycolysis. It operates in red blood cells of humans and other animals. Now, what is happening in this pathway, guys? Now, guys, you already know what is happening. Whenever the glucose, it is entering into the RBC. It is getting entered into the RBC. Now, what is happening in this RBC? It is going into this RBC. Now, what will happen in this RBC? This glucose will be converted into glucose 6-phosphate, right? Now this glucose 6-phosphate will be converted into glucose. Yes, you already know it is okay. It will be getting converted into fructose 6-phosphate, right? Fructose 6-phosphate. This fructose 6-phosphate will be converted into fructose 1,6-bisphosphate, right? And this will be now getting converted into two things, right? The splitting reaction takes place and we have glyceraldehyde 3-phosphate. You already know glyceraldehyde 3-phosphate. Glucose has how many carbon, guys? 6 carbons, right? Now we are adding glucose at 6th place. We are adding phosphate, guys. And that phosphate, it is coming from this ATP only over here, right? ATP converted to ADP and one phosphate is added to this glucose. Now this glucose basically changes into fructose phosphate. Fructose is also having the 6 carbon only. Okay, we have the same molecular formula, but different structural formula. Obviously, these are the isomers over here. Now, this fructose 6-phosphate will change into fructose 1,6-biphosphate. Now, what is happening over here, guys? Again, yes, fructose 1,6-biphosphate. We have 6 carbons. At 6th place, there will be phosphate, and also we are having phosphate at 1 place also. Now, this extra phosphate, it will again, the ATP will be utilized, which will be converted into ADP. Now, this fructose 1,6-biphosphate will be converted into dihydroxy acetone phosphate and glyceraldehyde 3-phosphate, means 3 carbon over here and 3 carbon over here, right? They're splitting. The 6 is splitting into 2. Now, this dihydroxy will be like changing into this glyceraldehyde 3-phosphate. These are like isomers, obviously. So glyceraldehyde 3-phosphate will be now 2 molecules. As you can see, glucose is directly shown converted into this glyceraldehyde 3-phosphate. It is like 2 molecules, guys, because dihydroxy also converts into glyceraldehyde later on. So yes, now this glyceraldehyde will be changing into this 1,3-bisphosphoglycerate. 1,3-bisphosphoglycerate. Obviously, it will be 2 molecules now. Now, what happens? This 1-bisphosphoglycerate basically Yeah, what will happen? There is an enzyme which is present over here that is called as 2,3-bisphosphoglycerate mutase. Now, when I say mutase, guys, you already know what is happening. This 1,3-bisphosphoglycerate, it is basically having this 3 carbon, 1, 2, and 3. And the phosphate is added to third carbon and first carbon. That is 1,3-bisphosphoglycerate. Okay, 2 molecules of this are there. Now, what is happening, guys? It is converting into 2,3-bisphosphoglycerate. It means it has the same molecule, but this time the phosphate from the first position, it is shifted to second position, right? Phosphate from one position, it is shifted to second position, guys. So that is 2,3-bisphosphoglycerate, and it is getting basically what happens, guys. This step is bypassed over here. Over here, we were getting one ATP, we are not getting that, and basically this 2,3-bisphosphoglycerate converts into 3-phosphoglycerate, and it again this 3-phosphoglycerate will be converted into 2-phosphoglycerate. You already know phosphoenol pyruvate, and it will be converted into pyruvate, guys. It will be converted into pyruvate. So basically, what is the significance of this 2-phosphoglycerate? Basically, now, what is the significance, guys? You already know it allows the glycolysis to proceed without synthesis of ATP. Basically, what is happening, guys? You already know if the step is bypassed, guys, over here, the 2 ATPs are utilized, right? And 2 ATPs which are formed from this phosphoenol pyruvate, right? So they are like 0, right? But so 2 are utilized and 2 which is produced, it is getting 0. 2 minus 2 is 0. So basically that there is no net gain of ATP over here. Okay. So basically it combines with the hemoglobin, guys. You already know this 2,3-bisphosphoglycerate combines with hemoglobin and reduces hemoglobin affinity with the oxygen. Now, what happens? This will help in unloading more oxygen to the tissue. So this combination is basically broken down so that oxygen can be delivered to the tissues. And that is the ultimate significance of this 2,3-bisphosphoglycerate, right? So that is the Rapoport-Luebering cycle. That is the Rapoport-Luebering cycle that you have to remember from the exam point of view, right? First, you have to define this. All these steps you have to write down, but after drawing this particular flowchart. And if you just try to show every step, it will be best, guys. It would be best. Site, organelle, the series of step, how the net gain is there, and ultimately the significance. 2 lines about the significance you have to write whenever there is a note. Definition, the process in the form of a flowchart, the reactions, and the energetics along with the significance, guys. That is something very much required in an essay writing, right? So that is the next question that we have already discussed. Now, coming on to the next question, that is, yes, again, the significance of the HMP shunt pathway, guys. The significance, yes, of the HMP shunt pathway, or we call it as the hexose monophosphate pathway, right? We call it as hexose monophosphate pathway. And now, guys, we are going to discuss what are the significance, right? Now, guys, if like, okay, let us just little bit discuss about this hexose monophosphate pathway. Monophosphate pathway. Now, when I say hexose monophosphate pathway, it is also known as pentose phosphate pathway, pentose phosphate pathway, or Dickon-Hoereker pathway. Okay, so like no need to remember that much. Dickon-Hoereker pathway, or pentose phosphate pathway, or hexose monophosphate pathway. Now, basically, where this is occurring, it is occurring in the cytosol. Okay, it is occurring in the cytosol. Now, guys, what is happening in this? We have like 2 phases, guys. We have 2 phases. The oxidative phase, if we talk about the steps, right? We have like 2 phases, oxidative and non-oxidative. Non-oxidative. In oxidative phase, you already should know it is irreversible. It is irreversible oxidative phase, and it helps in the production of NADPH, the major source of NADPH. NADPH. Now, what is the significance of this NADPH, guys? This NADPH, okay, it helps in the reductive biosynthesis reductive biosynthesis of fatty acids and steroids, right? Even cholesterol. So now places or the organs where this oxidative phase occurs, where this oxidative phase operate, you already know it is liver, right? It is the adipose tissue, guys. You have to remember adipose tissue, gonads like the ovaries, okay, the lactating mammary glands, the lactating mammary glands, right? Even guys, remember the thyroid glands, even the thyroid glands, right? So basically, it helps in the reductive biosynthesis of fatty acids, steroids, and cholesterol. So it is the first phase, that is the oxidative phase. It produces NADPH, and it helps in the reductive biosynthesis of this, yes, fatty acids. Apart from this, NADPH has also one more clinical significance. So this is the hexose monophosphate pathway. It is producing this NADPH, which is the first function is the reductive biosynthesis. Apart from that, it is needed for free radical scavenging. Very important. Free radical scavenging. Basically, it is important in RBC. You already know free radicals scavenging. It is important in RBC to maintain membrane integrity of RBC. To maintain the membrane integrity of RBC. Integrity of RBC. Even this free radical scavenging, it is very much important in the lens, right? Why? To keep the transparency of the lens. To keep transparency of the lens. Okay, so basically it is also converting this free radical scavenging HP to, it is not letting HP to convert into meth hemoglobin. Okay, basically HP we have iron +2, in meth hemoglobin we have iron +3 state. Okay, so basically it is helping it in the reduced state only, right? So that is something, it is important in RBC or erythrocyte. So that is like that you have to remember: free radical scavenging, reductive biosynthesis of fatty acids, steroids, and cholesterol, and organs where this take place. This is something which you have to mention. Now, guys, apart from that, guys, you also have to remember the non-oxidative phase. Now, non-oxidative phase, it is basically reversible, guys. It is basically reversible. And in the non-oxidative phase, basically it produces pentosis. It produces pentosis. Now, this pentosis, guys, remember, now, okay, this pentosis, you already know they are basically, no, these pentoses are basically important for DNA and RNA synthesis, right? So these pentoses are important for DNA and RNA synthesis. DNA and RNA synthesis. So these are basically the important like the significance of this HMP pathway. So pathways operating, I've already discussed RBC lens, obviously, right? So NADPH, glutathione reductase, it is generated with the help of NADPH, which help in free radical scavenging, guys. Very important. RBC membrane integrity, we have already discussed, right? So basically, ATP is neither utilized or produced, and you have to remember NADPH is also required to keep the iron of hemoglobin in the reduced state. I've already told you in Fe+2 state, it never lets this hemoglobin converted into the meth hemoglobin, right? So that is something you have to remember. All the important concepts regarding the significance, and you can see that it has been asked in December 5 revised schedule 2, January 8 revised schedule 2, January 8, January 12, like multiple number of times. The importance has been asked, guys. The importance has been asked, and that is something you can take away from my particular point, right? We have two phases: oxidative, non-oxidative. Non-oxidative produces pentosis, important for DNA and RNA synthesis. Oxidative produces NADPH, right? Free radical scavenging in RBC to maintain membrane integrity, right? Lens to keep the transparency of lens and help to keep the hemoglobin in reduced state, right? Apart from that, it helps in the reductive biosynthesis of fatty acids, steroids, and cholesterol. So that is regarding this. Now coming on to the von Gierke's disease. Now von Gierke's disease, guys, you already know we have already discussed this von Gierke's disease, but let us just try to see what all important points are there in this von Gierke's disease. And we have already, like, I just wanted to show you what yeah, in this von Gierke's disease. Hmm. So you can very well see over here, this glucose 6-phosphate is converted into glucose with the help of enzyme glucose 6-phosphatase. Now, guys, remember, if this glucose 6-phosphatase is not there, if it is absent, enzyme deficiency will be glucose 6-phosphatase. Glucose 6-phosphatase, if it's absent, it will not be able to cut this phosphate. If enzyme ही नहीं है, now what will happen? Glucose will never be formed. Now let us just try to write about this von Gierke's disease, how to write down this in exam, right? So yes, von Gierke's disease, and it has been asked in December 17, revised schedule 3, and December 99. Now let us just try to see over here, guys. Von Gierke's disease, it is also known as type 1A, especially the glycogen storage disorder. Glycogen storage disorder. Type 1A glycogen storage disorder. Now, remember, guys, it is the most common. I'm writing most common. MC means most common glycogen storage disorder, right? Now, what is the biochemical defect? Biochemical defect. Now, guys, what is happening, guys? You already know glucose 6-phosphate is converted to glucose with the help of enzyme glucose 6-phosphatase. Now, phosphatase is an enzyme which helps to, like, omit or to break this phosphate bond. But this phosphatase enzyme, so basically what we are having, we are having defect in this glucose 6-phosphatase enzyme. Now, obviously, what will happen? Now, if this enzyme is deficient, what will happen? There will be increased levels of glucose 6-phosphate, and glucose will be automatically decrease. Yes, glucose will be automatically decreased. So we have increased glucose 6-phosphate and decrease glucose. Glucose banega hi nahi. Obviously, this enzyme is absent, so glucose will not be formed, right? So now what will happen, guys? What will happen? Now, how this patient presents to you, guys, how this patient presents to you, you should remember, guys, what are the clinical features? This will be a 3 to 4 month old child, right? With doll-like faces, right? Doll-like faces. बिल्कुल गुड़िया जैसे, it's just like the doll with very thin extremities. Obviously, glucose is not there. So all the extremity, okay, the upper limb, the lower limb will be like very, very thin with thin extremities, right? Apart from that, the size of the liver will be increased, right? There will be more glucose 6-phosphate. There will be massive hepatomegaly, okay? Again, there will be no splenomegaly, guys. The size of the spleen is normal in this case. There will be, yes, renomegaly, guys. Renomegaly, guys. Obviously, reno means the size of the kidneys will be increased, and that is the characteristic feature of this particular disorder. Characteristic feature. And guys, remember, there will be milky white plasma. Milky white plasma, and that is due to the triglycerides. Because of this triglycerides, yes, we have this milky white plasma. Obviously, it will not be converted into glucose. The plasma will be looking like this milky white. Now, we have done the clinical features, guys. What is the biochemical hallmark? Biochemical hallmark. You already know, guys, if there is decreased levels of glucose, it will be something leading to hypoglycemia. Hypoglycemia. We will have lactic acidosis. Obviously, lactic acidosis. Hyperlipidemia. Hyperlipidemia. Triglycerides will be more in the blood. Emia means blood. We have ketosis over here. right? We have hyperuricemia, okay? Hyperuricemia over here, right? So that is you guys will always see fasting hypoglycemia over here, fasting hypoglycemia over here, right? Now you already know if there is more glucose phosphate, guys, if there is more glucose phosphate, what will happen? This glucose phosphate will enter anaerobic glycolysis, anaerobic glycolysis, right? And this glucose phosphate, okay, will be converted into pyruvate and it will be converted into lactate. So there will be lactic acidosis also. There will be lactic acidosis because of more glucose 6 phosphate, not this glucose 6 phosphate is not more glucose 6 phosphate, right? Glucose 6 phosphate will be more, right? It will be more, it will be entering an anaerobic glycolysis, converting into pyruvate, and pyruvate will be converting into, yes, lactate. Yes, that will. Now, why this hyperuricemia will be seen, guys? Hyperuricemia. You already know we have increased glucose 6 phosphate, right? Now, what will happen? This glucose 6 phosphate will enter HMP pathway. It will enter which pathway? Hexose monophosphate shunt that we already discussed. Now, what will happen? It will increase in pentosis. We already discussed that the non-oxidative phase, okay, that will be releasing these pentoses that is required for the synthesis of RNA and DNA. Increase pentosis, okay, what will happen? Yes, RNA and DNA, basically they are made up of purines. So there will be increased purine degradation. And you already know if purines are degraded, what will happen? Uric acid will be degraded, will be coming out in urine, and that is hyperuricemia. Hyperuricemia, guys, right? Hyperuricemia. Now, guys, you already know. Now, guys, ketosis. Why ketosis will be there? Why ketosis will be there? Let us just try to discuss why in a patient of von Gierke's disease ketosis will be there. Guys, you already know there is hypoglycemia. Hypoglycemia. Now the body will try to generate more glucose. The body will be trying to generate more glucose. Yes, the body will be trying to generate more glucose, right? So there will be increased gluconeogenesis because glucose is not coming from this. So there will be new methods of generating the glucose, increased gluconeogenesis from oxaloacetate. Now this, if oxaloacetate is depleted, what will happen? Beta oxidation will start of fatty acid. That is again one. Okay. Now what will happen? There will be increased acetyl coenzyme A, right? Now acetyl coenzyme A cannot go into TCA cycle because oxaloacetate is already depleted. So this acetyl coenzyme A has to go into ketone body synthesis. Ketone body synthesis, and that is something referred to as ketoacidosis will take place, or ketosis will take place in this, right? Now that is how the patient will present with ketosis also. And why hyperlipidemia, guys? Why hyperlipidemia? You guys already know that this glucose 6 phosphate can enter aerobic glycolysis also. Okay. Aerobic glycolysis, we have increased pyruvate, we have increased acetyl coenzyme A. Now this acetyl coenzyme A cannot go to oxaloacetate because it is already depleted. It cannot enter TCA cycle. So this acetyl coenzyme A will be going to, yeah, fat will be releasing this fatty acid synthesis will be taking place, and glycerol. And this fatty acid combining with glycerol will result in the formation of triacylglycerol or triglycerides, hyperlipidemia. And that is why the von Gierke's disease patient, the plasma is milky white. That is due to the deposition of this triglycerides. And how it is coming, you can see this glucose 6 phosphate, right? So that is again, guys, how you have to write about this biochemical defect, guys. You have to write the clinical features, right? You have to write the biochemical hallmarks, and how this biochemical hallmarks are taking place. You have to just mention over here. So that is the another question, that is von Gierke's disease, right? Now coming on to, yeah, this was the last question for today, and thank you for watching. Thank you for your patience, for listening me out. These are the social media handles, guys, for you can follow this for the upcoming schedule. Okay, schedule. And yes, thank you.